All right, Algebra 2. We are going to be looking at some more functions here, and this might not seem like it, but it's actually kind of a continuation of what we were talking about on Monday or Tuesday with that polynomial triples activity. All right, so the whole idea about what we're going to do here for the rest of the semester is we're going to start talking about some of the basics that we've been doing with other functions, but these functions are going to have higher exponents than we've had before. So what I mean by that is all of what we did here in chapter 4 is we really dealt with x squared problems. Okay? At the very beginning, we learned a lot about their features, vertexes, axes of symmetries, domains, things like that. Towards the middle, we learned some processes that we could do with them, especially factoring. And then towards the end, we really learned how to solve them or find their x-intercepts. All of those same things can be done. They may not have vertexes, but here in chapter 5, we're going to be looking at x to the third, x to the fourth, and x to the fifth as our leading exponents here. Now, one thing to note is that these numbers, these exponents, the biggest one in a problem is called the degree. All right, so the degree is what we just call the highest exponent. Highest exponent right there. All right, and that's going to be helpful as we kind of go on a little bit further. All right. When we're looking here at what's going to take place, the first thing we're going to do is we're going to start talking about properties of polynomial functions. Okay, and this big thing right here is just a turning point. A turning point is when the graph changes from increasing to decreasing or vice versa, right? So we're going to take a look at that when having some graphs. One of the things that we're going to do here is not be asked to graph them by hand, but anytime that we are looking at features of a graph, we are just going to use some type of a graphing calculator or Desmos to make that happen. So one of the things that you might need to have available here is Desmos. All right. Now, one of the key things with any polynomial function, anything that's higher than just an x squared, is this idea about end behaviors. Okay? End behavior is the idea that depending on the features, what happens on the far left and the far right is really going to just depend on some of the features, right? The degree or the highest exponent, and also what the leading number is, right? So like if it's 3x squared, the 3, that leading number right there. So here's something that we've really seen kind of simplifying this, right? An even degree, something that we've seen before. Right, this would be like a positive x squared, right? So we've seen that before. This end behavior, what happens is, and if we think back just to a regular x squared graph, on the far left, right here, and on the far right, every single time it went up and up, all right? So that's what we call this feature. If it's a even degree and a positive leading coefficient, we say that the end behavior is up and up. The left side goes up. Oops, meant to make that a highlighter, sorry. And the right side also goes up. Okay? And notice I've color coordinated that with a parabola here. All right? Let's do the same thing here. The one right below it, where it's an even degree, but this time it is a negative leading coefficient, right? It's a negative leading coefficient. This time, again, an example of this is just negative x squared. So anytime it has an even degree, maybe negative x to the fourth, maybe like we just said, negative x squared. But a negative number at the very beginning of that, a down and down is, right? So again, an example of that would be an upside down parabola. The negative sign would flip it upside down. What we do here is we just call this a down and down. Again, the left side goes down, and so does the right side. It also goes down, right? So there's the left side there, the left side, and the right side there. Okay? Now, this is important here, especially when we move on to higher levels of math, because more and more complex functions, it's really hard and just not important to know every single detail about a graph. What's more important is knowing some of the key characteristics, a la this end behavior, maybe some other things that we're going to talk about a little bit later as well. All right, an example of this one in the top right. The top right, you can see here, if we look at it, we notice that we are going to take a look at it being an odd degree here. So an odd degree and a positive leading coefficient, something like that, is just a line that we've seen, right? So maybe like just an y equals x or 3x, right? The degree is odd. Again, the number that I'm circling right here. And red is just an odd number, x to the first power. And 3 is a positive number. So if I were to graph something like this, it would just be a line. Notice on the far left, it goes down, and the far right, it goes up. What we call that here is a down and up. All right, one last one here. And there's really only one combination that we have yet to explore. Excuse me. That's an odd degree and a negative leading coefficient. So if I look at the combinations here, really the only thing I haven't done is what we call an up and down, right? And that's really anything with an odd exponent, but it has a negative number in front as the leading number. So like maybe it's negative 5x. Again, that number that I'm circling here, the exponent is just odd. So again, an example of how I might graph that is just a line, but it has a negative slope. Keeping things true here on the far right, it's going down. On the far right, or the far left, excuse me, is going up. All right, so you have a chance. It's always going to be multiple choice. Now, I will say that in pre-calculus, they are going to use different words. They're going to use more of the infinity idea. But for us right now, just kind of getting used to this, I think that these four, and I'll put the blue stars next to them, just so we can see it clearly here. This right here is one answer, up and up. Down and down is another answer. Down and up is a third, and up and down is a fourth. All right? So those four answers are answer choices that we could do. Now, one of the things that we're going to do here, you notice that on example 2, we're looking at equations that have a higher exponent than a 2 as the biggest one. Okay, and so what happens here is we've looked at factoring before in previous ones, but something we've never had to do before is pull a GCF out that was a letter. So if I just pull a GCF out, right, they all have an X, in the original problem. And then what I can do is I could just keep going, right? I always want to factor something completely. Factoring is a really helpful tool because what it does is it allows us to break down an expression or an equation into more simple parts. You might recall that when we factored it with just an x squared, those numbers or those factors related to the x-intercepts, and that same thing is going to happen here. But for right now, we're just factoring it. So it looks like right here, this would be what we need to get our final answer here. Right there. All right, same thing here. Try pausing this video. Again, pull a GCF out, and then just keep factoring it as necessary here. All right, pause this video, and then go ahead and see what you got. Make sure that when you have this, pull the GCF out, this placeholder of a 1 has to be there at the very end. Notice it's written like this. If we do see 2 of the same thing, really the way that we should be doing this is we should write it squared. So I have a 2x and then the quantity x minus 1 squared. Okay. All right, let's keep on moving here. Finding zeros of polynomial functions. All right. So here's what we remember. And now this is kind of something that I had mentioned earlier in example 2. Remember, anytime we have a factor, right? And so this right here is what I'm talking about when I say a factor. Right here, this expression right there, just x plus a number or x minus a number, and the different names for the x-intercept, right? So again, we talked about all of those names as well. What are the zeros of these 3 right here? What are the zeros of this, right? So remember, if I'm trying to find zeros, y has to be 0. So again, I could set that up for 3 separate equations. So it's -2, +1, and +3. So again, we're not going to have to do this by hand here. This is just a simple sketch just to kind of build the function. But you can see that right here is -2, right? Because we know it's an x-intercept. There's +1, and then also +3. Now, what step 2 says, find some points between the zeros. So really what I want to do is I want to test to see, does the graph, start and go like this, or does it go up between 3 and 1 and down between 1 and -3? What is that graph really going to do here? All right. So what I'm going to do here is just to find some points between. So what I'm going to do is I'm just going to plug a 0 in. So I'm going to go back to this original problem here. And I'm going to plug a 0 in and basically just do the math. Now, honestly, I'm really just concerned if my answer is going to be positive or negative. So if I plug a 0 in for each of these, that would be, again, let's see if I can write this down here. X equals 0. So I'm plugging the 0 in. That's going to be a 2 here. That's going to be a -1 in the middle and a -3. What my answer is for that is just a 6. So that means right here that the graph is going to go up. I could plug a 2 in and see what happens here. So again, I could plug x equals 2. And if I do that, I got a 4 in the first parenthesis. I get a 1 in the second. And I get a -1 in the last one. So that's just a -4. So I'm going to know that it's going to go up. Now, I will say this. It's got an end behavior here, and that's step 3. Think about it. Do I have an even amount of x's or an odd x? Right? So think about this. When we're looking at the degree, we're always thinking about the equation, which is right here, in standard form. And so if I were to distribute that, that would be x to the third. So it's odd, and it would be positive x to the third. So my end behavior is odd and positive. So if you recall, that was a down on this side, a down on this side, and an up on that side. So that's kind of a rough sketch there. Again, it doesn't have to be completely accurate. Notice that for my red here on step 2, I got 0,6, and I don't even graph it up to 0,6, right? I'm just trying to show, does it go above or below? And the same thing with the blue, right? 2, I got a -4. Again, it doesn't necessarily even go to -4. All right? So B, it's asking here kind of a little bit of more simplified version. What's the degree of this polynomial? So again, how many x's? So the degree would be x to the 4th, because if I multiplied it all together, that's what the leading term would be, x to the 4th. Okay, I could tell that just by multiplying or distributing it all together, right? I'm not actually having to do that, but if I did, it would be x to the 4th. Now think about it. It's actually going to be the leading coefficient is going to be a negative number here. -2 times 1 times 1 times 1 is just negative. So it's an even and a negative. That should be a down and down here. We've already found the zeros of the function in a previous problem, so let's do it again here for the last part. Now remember, it's basically setting each factor equal to 0. So when I look at this one right here, my answer should be 0, right? -2 times what is 0? When I'm looking at the next one, I should get a 4. Again, that comes from this one right here. That comes from this one right here. X minus 4 is just a 4. Next one is -6. And again, that comes from this one right here. Just a -6. And last but definitely not least, 9er. And that comes from this expression right there. Okay, so those are the 4 zeros that we would have for that problem. Let's see if we can go backwards, right? Instead of starting with the parentheses and then getting to the answers, what if I'm already given the answers here? What if I'm already given the answers? Notice what's happening here. I'm already given the answers. So if I take these 3 numbers here, this would be x plus 2. This would be x minus 2. And this would be x minus 3, right? So again, how I'm getting that is just kind of going the backwards way from that. What I can do here is I could distribute it. Remember, you can only multiply 2 at a time. So if I have my 3 parentheses here, I know that the first 2 right here are just going to multiply to be, oh my goodness, x squared. Let's see if we can get a better job of drawing an x here. X squared minus 4. And then I have an x minus 3. So again, I could just distribute. It's x squared times x. That's x to the 3rd. X squared times -3 is -3x squared. -4 times x, -4x, and then -4 times -3 is just positive 12. So that's going to be our final answer here. A quartic, it is a little bit more intense. It's the same idea here. Again, there's my answers, my zeros, my x-intercepts. But what it's asking here is to write them as factors and then go ahead and distribute. So we'll say the distribution for a little bit later, but those are the factors that you would get, okay? All right, this next topic here is a little bit more intense, but what happens is sometimes, and we've actually seen this a little bit with the x squared graphs, but this idea called multiplicity, right? So the multiplicity is something that really comes into play in how it shapes a graph. So notice if a 0, notice that's in parentheses. So if an answer, if I have an answer and it happens to be an even number of times, then the graph does not cross the x-axis, right? So let's say I'm solving a problem, and we've seen this before where I've got a 2 and a 2. I know that it would just come, it'll touch the 2, and it'll bounce right back. All right, that's going to be a big feature of how this is going to look. So that's really what that means when it says an even number of times. All right. All right, so here we go. Step 1, we're going to factor this out just like we have. So it says x to the 4th minus 2x to the 3rd minus 8x squared. Let's go ahead and pull an x squared out. Looks to be the highest, or the GCF, excuse me. So if I do that again and continue to factor, it looks like it would be x minus 4 and x plus 2. Now here's what happens is depending on how many I have. So see how the exponent for the x is a 2? That means the actual answer is a 0, but its multiplicity is 2. Again, for x minus 4, the answer is 4, but the multiplicity is 1, right? The reason for that is because it's x minus 4 to the first power, right? X minus 4 right here to the first power. Any guesses what the multiplicity of negative 2 would be? And it looks like it'd be a multiplicity of 1, right? So again, it's a rough sketch. Nothing, again, that you would have to really account for on a test or a quiz. But I can just go ahead and mark these. So it was 0 was one of them. It was positive 4. It was negative 2. And what's going to happen is because it's a 4th degree positive, I know it has to go up and up. And the way that this is going to originate is that at negative 2, it goes through it. It kind of bounces right there at 0. And then it goes like that. So it almost looks kind of like a W. And that's kind of one of the shapes that you can use for an x to the 4th, right? So x squares are parabolas. Most x to the 4th are W's. Now, again, we've been talking about that you could really use Desmos to kind of help us with this. But for example, 5, this is really something where it would be helpful. Anytime we're really looking for a relative max and min, we're really going to be relying on these turning points. Okay, so again, just to clarify, if we haven't really talked about what a turning point is, a turning point is something where it starts going from increasing and switches to decreasing here. So here's kind of what I mean. Let's see. Can I do this here? Yeah, this is a good way to do this. So let's say that I'm using this ruler and I'm starting on the far left and I'm just kind of working my way up. Watch what happens to the ruler here as I continue that. See how it flips and goes the other direction, right? And then as I continue to follow it, it flips here, and now it's going back up, right? And then again, it flips and goes down. So anytime the ruler flips from going increasing like a positive slope and then flips to go down like a negative slope, that's where we are going to be switching, right? So a relative maximum can occur when it goes from up to down, and a minimum just occurs from when it goes to a down to up. So just to clarify here, again, we would use Desmos to type in an equation in that. And like for this right here, sorry, don't mean to do that. For these 2 points right here, these are relative maximums right here on this graph. This right here is a relative minimum. Those happen also at turning points, right? So all of those are turning points, but a specific, they're more specific in the fact of them being relative maximums or minimums. All right, so we're going to finish this here today. That finishes the first 3 pages of the notes packet. And we will see you guys on Thursday.